Hi folks, it's Mike Barnes here again, this time to talk to you about alternating current, the electricity that we use every day and how it's made. I have on my little graphic here a picture of two of these atomic particles. You can see we've got this nucleus in the one and the nucleus in the other, and they're close to one another. And I showed this to you because I just want you to see that electricity is really the movement of these electrons bumping into each other. They bump into each other in their orbits around the outer shell, and when one electron moves out of that shell and moves into the shell of another, there's a small amount of energy that gets released. Now we know that electricity and magnetism are closely related. We don't quite understand how it is that this nucleus of these atomic particles, even though they're containing positive and negative, or actually neutrally charged particles, how the positives stick to each other. We do understand that these electrons, which are negatively charged particles, would be attracted to this nucleus, and we understand that in certain types of particles, such as conductors, that these electrons move freely back and forth. And that's really what electricity is, the movement of those electrons from that outer shell. Now, in order to further illustrate this, I have two horseshoe magnets drawn for us. Number one shows the positive of the horseshoe magnet at the top, the negative at the bottom. And on magnet 2, we've got the negative at the top and the positive at the bottom. And I've also drawn handles on each of these magnets so that if we were to hold on to them and negative and positives are together, we would see that they in fact attract one another. So let's refocus our attention on these two horseshoe magnets. We know that when one position is positive and the other is negative and they are lined up, they will attract. What we haven't talked about yet is what happens when they are the same polarity, when they have the same charge. If magnet number 2 is also positive here, and magnet number 1 is negative at the bottom, magnet number 2 is negative at the bottom, they will repel one another. Let's put little collars on these handles of these magnets so that they can freely rotate, but let's picture that the columns are actually pinned to the wall somewhere and allow the magnets to rotate freely. If they are in this position, because they will want to repel one another, one of these magnets will tend to spin a certain direction so that you would have positive lining up with negative, and up here the polarity then becomes a negative polarity. And again, the magnet's in a position now where the positive and negative would be attracting one another. So we're going to keep magnet number 1 exactly as it is. But number 2, we're going to actually change the property of this shape. We're going to just create an iron core that looks like a magnet, but we are actually going to create an electromagnet. We're going to do that by taking wire and wrapping it around this iron core. Back down the magnet, wrap it around this side, and back down here. And then, in order to create a magnetic field around this iron core, we're going to just use a standard 12-volt battery. Picture your car battery here. It's got 2 posts on the top of it. One of those posts is going to be positive. The other post is going to be negative. And let's say we hooked these wires up to those posts. And when we did that, this pole becomes negative, this pole becomes positive, and voila! The two are attracting each other once again. Now, picture for just a second that I take these wires and I quickly flop them back and forth from positive to negative, negative to positive, and so on. You would see that this electromagnet, the poles would switch. They'd go from negative to positive to negative to positive, negative to positive, and so on. Down here, the same thing would happen. Positive, negative, and so on. And this magnet would actually begin to rotate over here. It would be trying to keep up with the negative, positive effect and rotate. Now let's get rid of the battery for a moment here and think about this whole concept in reverse. What I want you to do is think about an electric screw gun. If we had an electric screw gun and we took the chuck of that electric screw gun, battery powered screwdriver if you will, and attached it to that wooden handle. I'm going to draw this so that it has a little trigger, and let's picture this as the chuck of that screw gun, and I've got a little motor up here that drives that thing, and in a typical screw gun you've got your battery pack in here that drives the screw gun, and all I'm doing is drawing this to illustrate that we're going to turn this magnet with the screw gun. It's not pinned down, it's attached by a collar to the wall or some other structure, and over here this one is in fact pinned down. I should have showed that earlier. Let's put a pin in that, and now I pull the trigger on my screw gun and I get this magnet to start to rotate quickly. What happens over here on this other side? You guessed it. Out of these two leads, electricity happens. There's one final concept I'd like to show you about electricity, especially alternating current. If we were to look at this electricity generation on a graph, and at this position in the middle of our chart, we're at 0 volts. Up here at the top, we're at, let's call it a plus 170 volts. Down here at the bottom, I'm calling it minus 170 volts. You can now see how the waveform of that generation would look like this. This waveform is called a sinusoidal waveform, which is just a fancy way of calling it a sine wave when we're trying to predict how much actual power will be generated. We need to look at the amount that gets generated underneath of these curves. And we need to note too that because of this spinning magnet effect, we have our voltage going very positive, and then it crosses the 0 location here, 0 volts, and then goes down to a negative 170 volts here, and finally back up to a 0 volts here. Each time that magnet revolves one time, you have one cycle of electricity that gets generated. And it's shown in this waveform here, the sinusoidal waveform. Now in the US, that happens 60 times per second. In other words, the magnets are stationary, but the iron core that is spinning in many of these alternators that create electricity in the US, they're spinning at 60 revolutions per second, also called 60 hertz. Hz. In Europe, they're spinning a little slower at 50 hertz or 50 cycles per second. And what I want you to just note, this is for further discussion, is that in this single phase of electricity, this one magnet phase, if you think about it, we are actually at a point 2 times during the cycle where voltage equals 0. V equals 0. This is an important concept to understand for future discussions about electricity. To wrap it up, I hope this diagram helps you to understand how AC, alternating current electricity, is generated.